Again, this is based on the new time change because we technically are supposed to start at 4:10. And from last time when we gathered together before actually the start of the class, we talked, at least for the people who were early, and basically we thought that maybe we should change it to 4 o'clock. I sent a communication asking if anybody objects. I did not receive any replies, so it's going to stick at from 4 to 5:25. There is no change for those of you coming to Physics 11. At least at this point, there is no change. So it says that it's time, starting time and ending time. So when this class is over, and if you are in that class, you will have to wait to the starting time, which is 6 p.m. basically, so that we can start that session. Anyway, so today we're going to cover the basically the chapter 2 from this course, basically, and there are some assignments. I think there is a quiz already for you guys that you're supposed to be doing. And I'm hoping that you guys will have a chance to go through this thing and make sure that you do it. And if you have any difficulty, please communicate. Do not hesitate in doing that, okay? There is an assignment that is due this Saturday, so please do not forget that the actual discussion has 2 components. The first component is your initial, first of all, input to it. Namely, you put your reply, which includes your information, the preferred way of how to be called, what you're hoping to do with this class, to give us a chance to know you more, or at least your peers to know you more. Yeah, Physics 11 is just a lab. Okay, it's the lab for this class, Darren. Okay. Again, for those who probably do not see how the participation is graded, the participation is graded based on the discussions, not the first week of discussion. Okay, the first week of discussion, as long as you log into Canvas and you start your work, I can tell from basically the statistics that they give me, but after the first week, I would not be able to tell. I mean, you could probably be not doing anything and I would not be able to tell. So from the second week and beyond, during the live sessions, we will go through 1 or 2 or 3 questions, and we're going to basically work those questions and finish and answer the question. So it's not going to stay ambiguous. Then when you go home, did you guys, did I lose my audio or something or what? Somebody can't hear. Okay, Michelle, probably you have a problem with your audio. Okay, let's type for Michelle that you have, everything is fine in here. Audio is okay here. Okay, so anyway, so let's go back into the participation. The participation basically is based on live sessions. In other words, there will be a prompt answered in the live session. Once you go in the discussion, you're going to just replicate the answer, that's all. You're not going to do any kind of detailed calculation or detailed demonstration or anything like that. You say, okay, there was one question today, here is the answer to it. That's it, okay? Before you post your reply, you cannot see what other people have done, so you can't really benefit from that. You have to do an initial reply first to the discussion, then you will see what other people have said, okay? Then you will have an idea of what have done. Please do not edit it, because I will see that you have edited it also, okay? So it's going to tell me that it was edited. So you can't just put anything nonsense in there and then come back later on and say, okay, they all said it's 12 and I put 5, so I'm going to go and fix it. So do not do that. If you do that, you're going to lose credit for that particular question. Okay, so that's basically in a nutshell what this is. If you cannot make it to the live session, the sessions are recorded, so you still can go and watch basically the session. That to give me basically a assurance that you're actually following, you're doing the work you're supposed to be doing. There are quizzes. This first quiz is kind of a short quiz, so it's I mean, it doesn't pull from a larger data bank, basically, but the next quizzes, they will have actually similar number of questions, but they will pull from a larger data bank. So there is actually a very, very good chance that no two people will have the same quiz. You will have very little, basically, crossover between the quizzes. So in other words, you really have to focus on your work. Do not rely on what other people are doing. For this particular quiz, probably it may not apply, like I said, but for the next quizzes, it's going to pull from a larger, I'm glad Michelle fixed the problem, the data bank, so that you'll have more questions. Does this sound right? At least for this particular week, the first week, you really did not have to do any kind of commenting on the discussions as long as you're in the class. But if you're not in the class, of course, you can comment. So what's the point? Okay, that's the first week. After that, then it's a different story. Okay, so that's the in terms of the overall things of where we stand, at least in terms of things. Okay, and again, let me go back to the assignment that is due this Saturday. Please do not forget to include your pictures. I saw a lot of people posting and did not include their pictures. Please go and revisit your post, delete it if need be, but you need to have a picture of yourself, okay? This class, Physics 10, has no lab. We will do demonstrations on the class, but we will not do lab. Physics 11 is its component for the lab. If you did not already enroll for Physics 11, I don't think that there is room for it right now, but down the road it may have some openings. It's a prerequisite for Physics 11 to have Physics 10. Either you did it in the past or you're doing it right now. Does this answer the question? Okay. Yeah, this class has no lab, okay? So you'll not be doing lab reports for this class. Okay, so let's start the chapter, unless you guys have any other question. No? Okay. So, question regarding our discussion points. I know it is due at the end of each chapter. Did I? No, there was no question. Again, Michelle, there was no question. I'm sorry, probably your audio was off when I was saying this point. This week, you do not have to have any kind of replies to the discussion following the chapters, okay? This week only, but next week there will be, okay? Does this sound right, Michelle? You're going to get your credit this week. Yes, Michelle?
Sorry, I was typing something, but I guess I'll just answer on the mic. So just to confirm, we'll still receive the 5 points without a submission. We're good to go?
For this week.
Okay.
For this week only. Okay. Okay. Okay, very good. So, so unless somebody else has a question, we're going to start this chapter. Okay. So again, this chapter, I need a confirmation that you guys are looking at the slide. At least one person. Yeah, because I hate to be, yes, very good. Because I hate to be right in the middle of a point and then somebody says, oh, we're not looking at what you're looking at. And that's really not good. So again, the chapter 2 deals with the first law of Newton. There are 3 laws of Newton, so that you know. The promise is the following. If you know all of these 3 laws of Newton, if you understand them, if you know how to apply them, okay, you don't need anything else. That's it. That's all you need. That's all you need. So today we're going to discover the second law. Next chapter, we're going to the first law, I'm sorry. Next chapter, we're going to discover the second law, which is actually the law, the most important law of Newton. And then the chapter after that, we're going to discover the third law. If you promise you know how to apply these laws forever and ever, and you know how to do them, technically there is no need for you to. Basically, you could attend the final and you should be fine. I mean, there are some problems that we need to address down the road and how to apply them, and this is what people do day in, day out, actually, on a daily basis. But these are the foundation. These are upon which everything is built, at least in our daily experience. What we do day in, day out. These are the most important laws that we have to use. Any engineer, mechanical engineer, any kind of field of engineering, for the most part, this is basically the laws that they use. They don't really go specifically and say this is the laws what you're using, but underlying all of this is a foundation of their work. You have to really be a scientist working with the extremely fast object, moving super fast, almost the speed of light, or near black holes, for example, supermassive objects, or near the sun for that matter, near supermassive objects, like for example, Mercury is very close from the sun, where these laws do not apply. Then in this case, you have to invoke relativity in that case. That should help you. This won't work. These laws will not be laws, actually. They're broken at that point. Or you're going to be with the very tiny, very small objects, like for example, atoms. When you're dealing with an atom, especially the electron and protons and neutrons, these laws also do not apply. You cannot apply these laws there. There is a big failure. You cannot do that. For example, you guys heard, probably some of you already took chemistry. You know that there is a nucleus which is positively charged, has protons in it, and the electron is in the outer shell. You might think, and we're going to discover these laws in here, that maybe we can describe them with these laws. Well, that's not possible because the electron and the proton have different charges and they should really attract to one another and they should collapse. You say, okay, how about if I push the electron and make it move faster and faster? Well, if you do that, it's going to radiate energy and lose energy and ultimately will collapse too. But we see that atoms are actually not collapsed. They're still intact and they work all the time. That's really an indication of the failure of this physics. Other than that, other of these two extremes, the super small and the super fast, these laws actually, they are it. This is it. So if you know them and understand them fully, the promise is that you will not really be confused about anything. You should be able to explain any phenomena. You should be able to solve any problems in physics in general, not just in this kind of a branch of physics which is called mechanics. Okay? So today, like I said, this is the first law of Newton. The first law of Newton is actually due to Mr. Galileo himself. I mean, when Mr. Newton, when he came in and he tried to formulate the laws of mechanics, he looked at the work of Mr. Galileo and actually restated it, that's all. And it became known as the first law of Newton. The reason why it's basically named after Newton, not Galileo, because Galileo was interested more in the motion of objects. He didn't care about what causes motion. Mr. Newton, on the other hand, was interested in what is the reason objects move to begin with. And that is where he came up with the three laws. So one of them was just a restatement of Mr. Galileo's work. So we're going to look first in the concept of motion itself through Aristotle, basically, and how his perception of motion was. His perception basically lasted for almost 2 centuries. It lasted for a long time. And it was wrong. So the fact that it lasted that long doesn't mean that it's right. It took the genius of Mr. Galileo to basically rework that and come up with better explanations for motion, descriptions of motion. He was able to calculate the force, the gravity, basically the pull of the Earth on objects. He was the first one to find the value of G, which is 9.8 meters per second. And he did a lot of work for us. He did so many things. At the end of his life, basically, he died in a house arrest because he believed in the work of Copernicus, in that the Earth was not the center of the solar system. As a matter of fact, he took a toy that people used to play with, namely a telescope, and he modified it, and he looked at the moon. And he looked at actually Jupiter, and he saw that Jupiter is made up with, at least there are 4 moons. The first night he saw only 3 moons, and the next night he saw Io, which is the smaller moon. Which, actually not small, it's a big moon, but it's very close from Jupiter. He didn't see it the first night. And that was a refute to the idea that the Earth was the center of the solar system, because that everything revolves around the Earth. Here is Jupiter with 4 moons revolving around it. So that was a major thing that he discovered. Of course, people later on basically did not like that. I mean, there was a lot of belief that this is wrong and it's against the teaching of the church and so on and so forth. So he was put in a house arrest. And if you read a little bit of history, he was basically excommunicated from the church, and he did not actually get any kind of recognition until in 1996, almost 4 centuries later. Okay, this story basically was in the 1600s when he was basically when these things happened to him. So that's basically in a nutshell the story of Mr. Galileo. In physics, because of his work, people refer to him as Big Man G. I mean, that's to tell you his value in terms of what he did for us and the work that he laid for us. So that's Mr. Galileo. Then Mr. Newton basically took those ideas and stated the first law of Newton, which is the subject of this chapter. We're going to talk about the concept of forces, and forces are vectors. If you did not have if you did not see what vectors are in the past, this is it basically. There are two kinds of, there are actually more than two, but at least at this point, we think we can classify quantities into two kinds. There are quantities that do not need direction and quantities that need direction. Quantities that are what we call scalars, numbers, okay? And quantities that this need scalars, but also have direction. If your friend, for example, is coming to your house, and you happen to live off of 91, for example, freeway, and he tells you, okay, I am on my way, I'm going 50 miles per hour. Okay? And you don't know where your friend is coming from which side is he coming from, Orange County, or is he coming from Riverside? Okay? So unless he tells you the direction, you will have no idea which way he's coming. So he has to tell you which direction on the 91 he's driving, or the 60, which way he's driving. So in other words, you have to have direction for some quantities, and velocity is one of them. Force is another, okay? The equilibrium rule, then we'll talk about the condition of equilibrium. There are two types of equilibrium. There is static equilibrium, and there is also dynamic equilibrium. So we're going to explore those two ideas. We're going to also talk about the normal force. This is the force that gets us tired day in, day out. This is the one we deal with on a regular basis. And this is an important force. Right now, probably most of you are sitting, and the only reason why you're sitting and not basically moving is because the normal force is keeping you on the chair. So that's really an important concept. And here it's calling it the equilibrium of moving things. I call that basically a dynamic equilibrium. That's actually the word used, static equilibrium and dynamic equilibrium. And then the fact that we are living on a planet that happened to be moving super fast. Okay, that is actually our we're going to talk about that, and there is some discussion why Mr. Copernicus, because he's somewhere in here between Aristotle and Galileo. Copernicus was the one who basically introduced the idea that the Earth was not the center of the solar system, but the sun was, and that is after going through a lot of data that that basically he was examining and things like that. He was hired actually by the church to fix the calendar, because by his time, the calendar that was done about 1500 before him by Ptolemy and all of the other people who basically used all the astronomical basically observations, Christmas was not happening in December. It was happening several months later, and Easter was not happening at the right time, and so on and so forth. So Mr. Copernicus was hired to basically fix the calendar. In doing so, he ended up basically correcting a lot of the ideas. And the basic one is the fact that we were looking at it all along wrong, in that the sun is the center of the solar system, not the Earth was. So, and for that, there was a lot of arguments against his approach, and he was himself was confused about it. He didn't know what to say and how to argue that this is correct, but he knew that this is the case. Until he died, basically, he allowed for his book to be published, and we will see the argument that he couldn't basically respond to, and that is really related to the concept of inertia that Mr. Galileo basically discovered after him. So this is in a nutshell this chapter basically, okay? Any questions so far? It's just the introduction of this chapter. Okay. So Mr. Aristotle had a lot of weird ideas. At least for right now, for us, we think that it's weird. I mean, Greeks are not known to do experiments. At least there was no anything documented about them to do to document experiments where they actually do the scientific process and so on and so forth. The only thing, per Mr. Feynman, that was documented that they actually did an experiment on is an experiment with light, basically, where you shine light on a surface, and the light is the phenomenon called the refraction, basically, where the light is broken down into an angle. Okay. That was, according to him, the only thing that was documented. They actually did several measurements and they put it on the table and we can look at it. So the same thing with Mr. Aristotle. So they basically, all of their experiments, they were thought experiments based on what we see without actually going and do any measurements. And then we come up with theories to explain things. They were more fascinated with mathematics and philosophy than actual hands-on physics like the way that we know it today. So his idea was that natural motion, he divided things into different kinds of classifications. Every object has a proper place determined by a combination of 4 elements: earth, water, air, and fire. Of course, we know today that this is nonsense. Okay, the fundamental elements are not this at all. Okay, any object not in its proper place. But remember, this lasted for almost 2 centuries. So this idea is held for a long, long time. People could not refute them because there was no way. You have to really have somebody who is super genius and super basically meticulous about things to go and prove that these ideas are wrong. And that was Mr. Galileo. Okay. So any object not in its proper place will strive to get there. So that's basically where things are. So stones fall. That's basically what his argument is. So if you take a stone and let go of it, it's going to fall, no matter where you put it. That's one of his laws. Puffs of smoke arise. So smoke always rise, so no matter how you do it. So this is some of the ideas that he came up with. Okay. And then straight and up and down motion. That's one of the things. So I really don't want to go into a lot of the things about these things, and especially violent motion and things like that, because we know all of these ideas are wrong. One of the things that was actually discussed extensively with him, and he didn't know how to answer it, basically Aristotle, until later on they came up with what looks like kind of an irrational argument for it, yet basically that was the only thing that sounded right, is this is an object in my hand right now, okay? If I push it, it's going to stop. I actually pushed it, it stopped. I pushed it, it stopped. I'm going to take another object. This one isn't, this is a battery actually. I'm going to do the same thing. If I push it, it's going to stop. It's moved actually and then it stopped. But ultimately it's going to stop. But one of them stops before the other. This object, for example, stopped before the other one. So they said, okay, what makes the first one stop more than the other one? If both of them have tendency to be at rest, these objects are supposed to be, their tendency is to be at standstill. So when you push them, they will try to go back to their normal state, which is not to move. So why one of them took less time to go and stop, and the other one took for a long time before it stopped? I mean, try this experiment at home. Okay, in this case, somebody said, okay, maybe it's the shape. Could the shape play a role? Well, you can make 2 objects of the similar shape, but one of them different sizes, and one of them will stop, the other one will not stop. Okay. How about the size itself? I mean, the mass, if you wish, what we know called today mass, inertia. Well, one of them probably will change the shape then. So when you eliminate one, you eliminate the second, you eliminate the third, there was nothing left for them to consider as really a reason for an object to stop, because it wants to stop. Versus another object that stops, both of them they do, but one of them takes longer time to do so. Well, he says, okay, the only explanation for it, and that was kind of weird, okay, and you'll have to wait for it to really, you have to really think about it, and probably going to make you laugh. Because this object, this thing, have memory. Some of them remember better than others. That's basically the only explanation they could come up with. I mean, it doesn't make sense, but that's what they came up with. And that, again, ideas lasted for a long, long time. So Mr. Galileo came up with several experiments, okay? A lot of experiments, and he did a lot of them, and he was patient. One of the experiments, he tried to actually measure the speed of light, which is kind of a fascinating thing, and we'll talk about that one. Remember, he did not have really a lot of the fancy tools that we have today. He did not even have a watch. Do you guys, can you guess what kind of timekeeping device he used to measure time? Any ideas? By the phone, he did not have. There was no sundial at that time. He did not have access to it. I mean, look, you want, I mean, somebody said the sun will give you a time of an hour or something, but you have a marble now, and you want to drop it on an incline, and you would want to know how long it takes. If you wait for the sun to go, basically go for a full hour, that was not precise enough for him. So the sun was not good for this experiment he was conducting. I mean, Terran is okay for larger time scales, for example, for a day or half a day or something. So you can use the time. At that time, he did not have a watch either. He did not have an iPhone. But the sun would not work for some of his experiments that required actually a little bit better. No, the pendulum at that time, no hourglass, same time. Let me tell you the answer, okay? This one, the pulse. That's what he was using. That's basically his watch, at least for the, because he knows he was able to time this one, how many it takes for them to go for an hour or whatever time it is. So he was using his pulse basically as a timekeeping device to measure the speed. Right now I'm trying to feel it. I cannot even, you have to really be very, very quiet. Remember in his time there was not too much noise. So right now we're living in a noise pollution. So, but in his time, that's his watch. He did not have access to an iPhone or device like what we do today. So that show you how much dedicated he was really to doing his work and getting the answers to his questions. So objects of different weight fall to the ground at the same time. This is provided with very little or no air resistance whatsoever. Of course, air resistance will impact the experiment. If you do it yourself and you go outside and take a feather, for example, and a hammer, and you let go of them in the same time, obviously the hammer will reach the ground faster than the feather because of the air resistance. But if you conduct the same experiment in vacuum, they technically should reach, well, not that technically, they will reach the ground at the same time because there is no other force to resist one object more than the other. So moving objects need no force to keep it moving in an absence of friction. Actually, he conducted another experiment, I don't know if it's in this notes or not, basically involving marbles and inclines. Let me see if I can get the tools in here. So he had an incline and he put some marble and he let go of the marble. He noted, of course, if we do this experiment ourselves, that the marble will fall, depending, of course, on this angle, the inclination in here. If it's small, and you have to have it small enough for his pulses to basically catch up with his experiment, because if you make the inclination high, it's going to come too fast, and probably the measurements will be not be as accurate. But it doesn't matter. That's how we found. That's one way of finding G, by the way. But you note where the marble will stop. So what he did then, he refined the surface. He basically made the surfaces smoother. You note then, if you do this experiment, that the marble will take a long time before it stops on the horizontal plane. Then you drop the marble from the same height, provided you're doing the same height, the same marble, or at least similar marbles to eliminate any kind of alterations and all of that. If you make the surface still finer still, the marble will travel even further before it stops. So he imagined that, look, if the surface and the marble do not interact by making sure there is zero, basically, interaction between them, which is the force of friction that we call today, then there is no reason for this marble to stop at all. So that's really the subject of the first law. Moving objects need force to keep it moving in the absence of, need no force to keep it moving in the absence of friction. So an object, if there is no friction, then it's going to go forever and ever and ever. Today, we live in an age where we have access to all kinds of devices and visualizations and movies and simulations and everything like that. It sounds something that we can easily basically relate to. In his time, it needed a lot of selling This was not something that people can be easily convinced with. In other words, if you discover a law tomorrow, you really have to basically make it bulletproof, basically make it sure that your argument is sound. And this was one of his experiments that, look, guys, if we do this time and time again, the only reason why it's stopping at all is because of this external force. And I keep on eliminating it by extrapolation, by basically making this, extending this idea to the point where there is no interaction, then this marble will not stop at all. So that's basically his argument on that. Okay. Yes. So a force intuitively is a push or a pull. That's basically what we think of as a force. Okay. You have to understand that forces do not require contact. I mean, when you push something, or you pull onto something, there is that at least thing that we can think of, and that is that there is a connection. We're pulling on something or pushing on something. You don't really have to have that for a force. For example, the Earth. What is my thing that I had in my hand? Yeah, the Earth is pulling on this object, even though there is no immediate contact between it and the Earth. So if I drop it, it's being pulled by the Earth. So that's basically, so the force can be of a push or a pull without having to have contact. So the contact can be there or not there. For example, if you bring two magnets and you put them with the same side facing one another, they will repel each other. As a matter of fact, if you try to touch them, they will not, because there is a repulsion there in this case. There is a push in that case. If you reverse one of them, then they will attract. You have to really hold them in place, otherwise they're going to stick to one another. So that's basically what the force is. Inertia is a property of objects to the change in motion. And it's somehow related to the amount of matter in it, to the mass. So inertia is a property. Every object has it, okay? Every physical object has it. Energy does not have mass. So you have, that's the only place where probably inertia doesn't exist. But inertia and mass are related. As a matter of fact, we put them equal to one another, okay? Both of them, you can express them in kilograms. That idea basically eluded a lot of scientists. Why they are so, numerically you can express them with the same number, and they look the same. It took actually the genius of another scientist, Albert Einstein, actually to come up with a rationale for that. So that's another thing for another day. Anyway, the concept of inertia in here, balls rolling down a slope will pick up speed. And of course, the bigger the mass, in this case, the less speed that they will gain. Again, they have tendency to gain less. The lesser the mass, of course, the more speed they will gain, the more acceleration they will end up with. If they are going upward, in this case, they decelerate. So this is an accelerate, this is decelerate. Those are just words we use. I mean, both of them, you can assume that the acceleration is a positive value and the deceleration is a negative acceleration, that's all. When there is no slope, objects will basically gain or lose no speed. So in general, the word motion is the word velocity too. So they are used exchange. I mean, this you can say motion or velocity, it's one thing. It's the same thing, basically, okay? The use of inclined planes for Galileo's experiments helped him do what? He discovered inertia. That saves the day for Copernicus. We're going to talk about that toward the end. That is the concept that Mr. Copernicus really needed to understand his idea. Okay, so he discovered the concept of inertia. That's really what it was. Inertia is a property of all objects, basically. So when we asked the subject of physics what physics studies, says motion. And last time, I think in this class, we talked about the example of the gorilla or cat. Gorilla is not really a subject of physics. I mean, you can, under some circumstances, put the gorilla as a subject of physics, but in general, it is not. However, A dead gorilla is a subject of physics. Dead cat is a subject of physics. So in a sense, you can treat them as long as, because gorilla, for example, or a snake, for example, it moves in ways that we cannot explain in physics because it has other forces subject to and other behaviors that we cannot explain. So inertia is a fundamental property. It's a property of matter. It's not a force. It's not anything. It's just a property. Okay. It's mass, basically, expressed in kilograms. So this is the statement of the first law. You have to know this law. Every object continues in a state of rest or uniform speed in a straight line unless acted upon by a non-zero net force. That's it. So you have one object. I need you guys to keep track of this one, because in the next chapter we're going to alter this diagram. And zero force, or no net force, basically. That's what zero force means. If that's the case, this situation is covered under the first law of Newton. So if all you have is one object, or a bunch of one objects by themselves, okay, you have one object in here, one object in there, one object in there, isolated from the rest of the other objects. And if each and every one of those objects is under no net forces, meaning there is zero force, or the forces they are canceling one another mutually. If that's the case, then that object is subject to the first law. And the first law states basically, if the object was at rest, it's going to stay there. If the object was moving, it's going to continue moving in a straight line with the same speed. It's not going to gain speed or lose speed, as long as the situation does not change, okay? As long as it's not all of a sudden subject to a net force. If it is, then this law will not apply. This law cannot be invoked. You only invoke it in this scenario. One object, zero forces, or no net forces. I mean, you may have forces, but they cancel each other. You may have three forces, but they cancel each other. They sum up to nothing, okay? Two forces are pulling on one side, and the other one is just enough to cancel the two, so that's it. They cancel one another. So if that's the case, then you're in good shape. You don't have a problem. A force is a vector quantity, and as I said before, a vector is really has a magnitude and direction. You have to have two things: magnitude plus direction. Driving 50 miles per hour will not tell me which way you're going, especially on a surface, okay? If you have a bird flying 50 miles per hour, and I don't tell you which direction the bird is flying, you cannot predict where the bird is going to end up after 1 hour. Yes, it's going 50 miles per hour, but you have no idea which direction it's going. It could end up in a hole, provided that it stays on the plane. If it goes up and down, then it could go anywhere. So you have no way of knowing where it's going. So direction in this case, velocity is a vector. Same thing with a force. A force needs magnitude. Expressed the units for force are Newton, and also and it has direction. So it has magnitude, which is expressed in Newton, and it has direction, which is expressed in which way the force is applied. Okay. Force is a vector, velocity is a vector, acceleration is a vector. Okay, we'll learn down the road about other vectors. Okay. This is as opposed to a scalar. Scalar is not a vector, just a number. So net force is basically the sum of the forces. You have to take into account the direction when you say sum. So when I say add two vectors, I don't really mean literally add their magnitudes only. I mean to pay attention to their direction also when you add them up. In this case in here, they have the same direction, so they add up. as you normally would add 5 to 5 and come up with 10. This two, when you add them up, you're actually doing the difference in this case, because one of them is pointing one way, the other one is pointing the other way. And this is a situation where this object is under no net forces. You're pulling it on it from both sides. So it's not going to go anywhere with the same force, basically. Pulling with the same force. So it's not going to go anywhere. Okay? So a cart is pulled to the right with a force of 15 Newton, while being pulled to the left with a force of 20 Newton. So you have 15 Newton to the right, and you have 20 Newton to the left. So the net effect is this extra 5 Newton to the left. So the correct answer should be 5 Newton to the left. Okay? Now, what is the net force acting on this object? You have 10 Newton to the right and 5 Newton to the left. So in this case, the two they subtract, because again, when I say add, I mean this is a vector addition. Vector addition is not like adding 10 plus 5 and say it's 15. This is actually a subtraction in this case, because both of them are in the same direction. So in this case, the answer should be 5 newtons this way. Okay, very good. So vector quantity has a magnitude and direction, is represented by an arrow. Sometimes they don't use arrows. If you're reading some books, for example, especially physics books or science books, they use sometimes a boldface. So this depends on the book. Sometimes they don't use arrows, okay? And you say, okay, the velocity is a vector. Why are you not using an arrow for it? Well, that's the choice of the author. Sometimes they don't like that, so they put a boldface on it to indicate that this is a vector. Now, on the other hand, on the opposite to that is the scalar. Like mass is a scalar. 10 kilogram is 10 kilogram. There is no direction for a 10 kilogram. Okay, take a bird, you weigh it, it's 10 kilograms. You can't tell which 10 kilogram bird. That's a big bird. Okay, I'm sorry. That's a 20-pound turkey, I guess. Okay, and so that's basically what it is. Volume, on the other hand, is basically also a volume. How much space how much it occupies out of the space. So that's also a number. Speed is also a number. So when you look at the odometer, that is actually the speed that you're looking at. You have to raise your hand head and look in the direction you're moving to come up with a velocity. Okay, so there are two things in the terms of the velocity. So the odometer will just give you the speed. It doesn't tell you which direction you're moving. Probably have to have a GPS in the car to tell you which direction you're going. Anyway, so this is basically some of the concept. Does anybody know of any other scalar? Can you think of another scalar quantity? Not a vector, scalar. We said mass. Length. Yeah, okay, the length is, you can consider it a scalar. The weight actually is a force, okay? Force down. But if it's just a number, remember every vector has a part of it that is actually scalar, namely its length or magnitude. So you can consider actually the length as a magnitude of a displacement or magnitude of something in there. So it's still time. Yeah, time is actually a scalar. Okay. I'm thinking in terms of temperature also. So if somebody tells you today the temperature is, I don't know how much it is in your area, but right now it's 80. Energy also is a scalar, you're right, okay? So temperature, energy, a lot of these concepts are actually scalars, okay, numbers. They are not actually, they're not vectors, okay? So good, you guys are top of these things. Glad to hear that. So a resultant, when you have two or more vectors, you want to add them, you have in this case what is known as a resultant. The resultant basically is coming from the word result, okay? So you have two vectors. If they are in the same direction, you just add them up. Just like you add the two numbers like we did before. So if this is one vector and this is another vector in the same direction, just add their numbers, that's it. If they're in opposite directions, the resultant in this case, which is the sum, is going to be the difference. Okay, subtract. But if they're at some angle in here, if this is one and the other one, you really have to use a parallelogram method to find the resultant. Okay, this is where the resultant is. Okay, for those of you taking physics 11, we'll do an experiment on that. Okay, we'll do a lab experiment on that. So this is the resultant. Okay, if they're right angle triangle, you can actually find the length using the Pythagorean theorem. So that's basically the hypotenuse is here, and this is the two sides. The sides square each side and add them up and take the square root. You will find the hypotenuse. That's basically what these things are. Provided that they are right angle triangle. If they are not, then you have to use different techniques to find the sum of the two vectors. So that's basically how you add the two vectors. Now, this is an associative property, meaning that if you have three or more vectors, you can add them basically two at a time. You add the first two, whatever resultant you end up with, you add it to the third, whatever resultant you end up with between these first three, you add it to the fourth, and so on and so forth. If I have a bunch of vectors, then the resultant is just add the first two, add the second, and then the resultant is going to just be straight out basically sum of the all. How many I have? 1, 2, 3, 4 basically vectors in this case. Okay, so that's basically in a nutshell what it is. Now, word of caution about vectors: when they are at 90-degree angle, you have to have this situation here. You have to have a 90-degree angle. There is a verbiage that we use in this case. Okay. The vector in this case, 50 newtons, of magnitude 50 newtons, I should say, is the sum of these two vectors, basically the 40 plus 30. Okay, that's correct. The 30 newtons, though, vector, this 30 newtons vector, is considered a component of the 50 newton vector. Basically, the 50 newton vector in this case has two components, which is the 40 newton vector, which is along the x-axis, and the y-axis you have the 30 newton vector. So that's basically, all of this terminology is correct, actually. That's exactly the verbiage we use for vectors. Vector can be expressed in terms of length and magnitudes. That's one way of talking about vectors. You can spend all day calling a vector magnitude and direction, magnitude and direction. Basically, give me the magnitude and the direction of the vector. And I give you that, you say, okay, that's a vector. Another magnitude and direction, here's another vector. Another magnitude and direction, here's a third vector, and so on and so forth. Or alternatively, you could talk about components. Give me the components of the vector. Then here is the x and y component, or here's the east-west, north-south components. Okay, so you can talk about the same vector with two different, basically, pairs of representations, either represented as magnitude direction or represented as components. It's equivalent. Okay, so the correct answer is all of the above. You can use magnitude and direction as correct, and also components is also another way of expressing vectors. So a vector can be expressed in different ways. Okay, it's the same thing, but it has different, basically, ways of showing itself, and they are all equivalent. It's not like they are different. They can go from one representation to another representation. Okay, here is Nelly, and she's hanging from the ceiling, and her weight is, of course, mg. It's mass times the gravity. That's the weight. That's mg. And we want to know the tension supporting her in the strings. Which one is higher? So what we do in this case, we try to break the force needed to balance her with on the two ropes to see which rope needs to be stronger than the other rope, basically. If they are different materials, which one needs to support more tension on which side? So that's basically the problem. So this is a statics problem. So if you're an engineering dealing with static equilibrium, or if you are going to go camping, for example, and you have your food, and you have weak ropes, and one of them is weaker than the other, and you want to hang your food, and one of them is shorter than the other, which one can you make it shorter? Or which side, for example, of the tree is closer, the other one is not further, and you want to hang your food to avoid that bears will eat your food. So you do that by distributing the weight correctly, by making sure that the ropes on the side, which side needs to be stronger. So you have a problem you want to solve, basically, in this case. You have a real problem. Okay, you're going camping, you don't want the bear to eat your food, and so you want that to be solved. So what you do in this case is, well, she's in equilibrium. She's not falling, she's not rising. So all forces must cancel on her, okay? Her weight is balanced by the sum of the two tensions coming from the two sides of the string. Because she's pulling down, then the force that balances her must be exactly opposite to this force and equal and opposite in magnitude. Basically, in this case, she's not going anywhere. The first law still applies to her. And the first law says, since this object is going nowhere, all the forces, the net forces, must be zero. That's what the first law is saying. So in order for me to find the component on this side, I draw a parallel to the other side. So I go in here and draw a parallel to it. I'm sorry, touching the tip of that force, okay? Let me delete the first one. Okay, so that gives me, as long as I stay parallel to it, that gives me, this is the component for that force. I do the same thing on the other side. I draw a parallel to the other one, okay? And see where it cuts the other side, basically. So this component is clearly bigger than the first one. So it's clearly, then the tension on the shorter side must be higher than the tension on the longer side, okay? And so if I have a choice, then in this case, I have to put the stronger cable on this side than on the other one, because the trees are far away from one another and our camp is closer to this side. So I want to hang my my food. I better do it in the right place. Otherwise I will lose the bear can get to it. Okay. Okay, so that's basically some of the examples that we're dealing with. A string holding a so again, we use strings all the time and masses and things like that to try to measure masses. Let me see if I can find something to measure here. I'm going to put my keys because I don't have anything to hang the other object in here, do I? Okay. This one has hardly any mass, so it's not going to matter in here. So I have a string in here, and I want to find the mass of this object. So I'm going to hang it. And I don't know if you noticed that, but the reading should be moving in here. Oops, the camera is, okay. The needle now should be moving, okay. So now this reading, this object now is at equilibrium. So in this case, this one stretched enough to give me a force in there. So what I measured in this case is how much change in length of this object went, and that is converted into units of Newton. So this device actually measures the force in Newton. I don't know. Oh, the image is backward. Okay, so you cannot see it. The screen flips the image. So see here if I can flip the image backward. Hold on, guys. Okay. What happened in here? Why is it not? Sorry. Okay, it's in newtons. I don't know. This object behind me is really making this thing not work well. Anyway, I'm just trying to demonstrate the scale that he's got in there. So the tension force in string acts upward. This is what we use to measure the force. We use this spring in here to measure the force. So again, the object is not moving, and that's how we're confident that the readings are correct in this case, and the readings are in Newton. There is another example in here of of workers in here, the net force, if this object is not moving, if everybody, I mean, I would neglect the horizontal motion, we're just talking about the vertical motion in this case. If all the forces cancel in this case, therefore the object is in equilibrium. So when we say sigma F, that's the symbol, the big capital, that's the sum of the forces equal to 0. That's what we mean in there. So this sum is actually a vectorial sum. So probably in this case, we didn't draw the vector on top of the F, but exactly it meant to be it. I mean, I told you earlier in the beginning that bold faces also are used to express vectors, not necessarily vectors on top of them. So the equilibrium rule applies to vector quantities, okay? That's basically what this concept is. Now we come to the concept of a support force, which is sometimes called the normal force. Actually, probably you will hear me use the word normal force more than support force. Is basically what keeps you sitting on your chair, what keeps every object basically in equilibrium. Now, if the chair does not exert enough force to keep you on it, it's going to fall. Okay? So that's basically if that's the situation. So if you exert a force on an object, that object will exert a force back on you, which is in this case the support force or the normal force, just enough to keep it from going. Now, if it's too much force, then in this case it's going to give in. Again, that's a static problem, so we have to really deal with that if we're trying to build buildings and things like that. So we have to make sure that we have enough support force to counterbalance the weight of the object that we're trying to support. Again, if you push on the spring pushes back. The book is pushing on the table is pushing back. That is basically what the support force. So the support force is not this one on the bottom, it's this one. That is the support force. This is the support force, okay? So you have to be very specific in here. So the normal force is this one. And it's called normal for a reason, because it's always perpendicular to the surface. So there is a surface assumed in here. So when an object sits on that surface, it exerts a force. Not because it does, because the Earth is trying to pull on the object. So in this case, the force has to be normal. If you tilt it, it's still normal to the surface. So no matter which way you look at it, so if the surface happened to be tilted and you have an object sitting in here, the normal force is always normal to the surface itself. That means this angle is 90 degrees angle. So that's why the word normal is more descriptive actually, because it gives you a sense of where it needs to go. So if the surface is tilted, inclined, then in this case, we know where the force is. It's always perpendicular to the surface itself, okay? Obviously, this object, if there is no friction, is going to start falling because, again, the normal force will not be, because the weight in this case will have a component in this direction. This component will balance this one, that's fine, but this component has nothing to balance it with, so it's going to start falling, okay? But in this situation, not going to move one way or the other because the two forces cancel each other. So the first law still apply. This situation is not the first law. So we cannot invoke the first law for this one because there is an imbalance of forces and net forces is not zero. Again, this is an example when you stay on the scale. The scale itself, all it reads is actually the support force, that's all. So when you say I'm reading my weight on a scale, I'm going to weigh myself, what you're actually reading on the scale itself is the support force or the normal force. Case in point, the following. If you happen to go on an elevator and the elevator takes off, during that initial motion, when the elevator is leaving the ground, it needs to accelerate. Now, your weight is pushing on the scale, but now, because of inertia, actually, your weight doesn't want to move, so it's going to move further back on the scale. So you feel actually yourself heavy. You don't have to look at the scale. You can feel that you're getting heavy. I mean, your stomach and everything else feels going down. Okay, so that's something. But if this, so basically at that point, the scale will read exactly the new number. It's not going to give you your weight. So for example, if you weigh 120 pounds or 140 pounds and you go on the scale and the elevator takes off, it's going to read an additional amount. Instead of 140 pounds, probably it's going to give you 147 pounds. So all of a sudden you gain 7 pounds. Okay, you didn't have lunch whatsoever, but you gained weight. Same thing. If the elevator comes to a stop, in that case, your body wants to keep on going, actually. That's the inertia again, the first law. But then there is less push from you now on the scale. So instead of reading 147, the scale probably could be reading now 132 or 133 or whatever that number is. So again, depending on the acceleration and deceleration, I should say in this case. So in that case, again, you feel like lighter, actually. You yourself, you feel like getting lighter and lighter, okay? Yes, for the correct answer for this one is half the weight, because the weight is distributed equally between the 2 points in here. So if you're 140 pounds is your weight, this will read 70 and the other one will read 70, because they add up both of them to cancel the weight of the person in here, which is what, 140 newtons or whatever. Okay. 140 pounds, 140 newton is nothing. 140 newton is 14 kilograms. That's the weight of my daughter's cat. Okay. No, 14 kilograms. That's not the weight. He's 14 pounds, 16 pounds. So it's more than that. Sorry, it's about 28 pounds or 30 pounds or something, which is bigger than the cat. So, now, equilibrium requires, like I said, there is a static equilibrium and there is dynamic equilibrium. As long as the net forces are 0, you will have equilibrium. Now, if the object is moving, in that case, it's going to continue moving with the same speed. So it's not going to change its speed. If the object was stationary, it's going to retain that speed. So if it was stationary, it's going to retain that stationary status. So it's static equilibrium. If the object was moving, it's going to continue moving with the same speed in the same direction, maintaining the sum of the forces equal to 0, meaning it's in equilibrium. Equilibrium means sum of the forces equal to 0. That's it. That's what equilibrium means. So you have two situations. Either the velocity is 0 to begin with, which means it stays 0, or the velocity is something, and it's going to stay that something in both direction and magnitude. Okay? So in this example, for example, if you push on the crate, and the crate maintains the same speed, it doesn't move. If it's not moving at all, then in this case, whatever you push, the friction is between the crate and the ground would be enough to counterbalance this thing. So try to push. I'm trying to push on the desk. The desk is not moving, but then that means that there is enough friction to counterbalance the force I applied. But of course, if I push hard enough, this desk starts to move. Okay, so there will be not enough friction to stop it from moving. So a bowling ball is at rest when is at equilibrium. That means sum of the forces equal to 0. When it's at rest, that's correct. It's at equilibrium. Or when it's moving steadily in the same line, with the same speed in the same line, same velocity. So the correct answer is actually C. Both of them are correct, okay? Now this girl is pushing with a 75 Newton. You push a crate at steady speed. The key word in here you need to pay attention to, steady speed. If the friction is 75 Newton, then how much do you need to apply? You need to apply exactly 75 Newtons to maintain this steady speed, okay? So the correct answer is 75 Newtons, I'm sorry. Here is the thing I was telling you about earlier of Mr. Copernicus, where the dilemma he was really, and this was a prevailing argument at that time. Here is the problem. They said, look, the Earth cannot be moving. If the Earth were moving, like you said, you're like Mr. Copernicus, you're telling us, the Earth is going around the sun. They knew then the radius, the distance between the Earth and the sun being about 150 million kilometers. It's a huge distance. In order for the Earth to go around the sun in 1 year, that means the Earth is moving super fast. As a matter of fact, it covers 30 kilometers every second. We started this class around 4 o'clock. Now it's a little after 5 o'clock. It's been more than an hour. We have traveled in space around the sun in that hour. Remember, an hour has 60 minutes and a minute has 60 seconds. So it has 3,600 seconds. That's what the hour is. We've been traveling at that speed of 30 kilometers per second for more than 3,600 seconds. So you do the math. 30 times 3,600. We've covered a huge distance in this hour. I mean, all of us were sitting in our homes, but because the Earth is actually moving, it took us into this journey. So they said to him, look, you have a problem in here. While the bird is sitting on the tree, it's moving with the tree, which is anchored to the Earth, which is where the worm is. So everything is moving at that speed. The minute the bird leaves the tree, trying to go and reach the worm, they said the Earth and the worm and the tree will leave the bird behind at that speed. Birds are not known to go that fast. I mean, they cannot do 30 kilometers per second. 30 kilometers is a huge speed. So in order for it to catch the worm, it has to travel super fast, and we have never seen that. This is not correct. So they argued that this is not true then, Mr. Copernicus, you're wrong. The Earth is not moving. Because if it's moving, this is the situation. As a matter of fact, if it's moving, according to this argument, the minute you jump up and down, the walls will hit you. The wall of the room where you are standing will move because you're jumped and you're freeing from being in contact with the Earth. So at that point, he was actually himself confused about this point. He didn't know how to make the case for it. But he knew, of course, he was correct based on his observations that the Earth is actually going around the sun. So that was the argument that he couldn't basically make. And of course, the answer to this one is very simple. Well, the bird right now is going 30 kilometers per second, just as much as the worm and everybody else is traveling with the same speed. While the bird is moving down, that motion of 30 kilometers per second is maintained by his body. So it's going to drift with everybody else because of inertia. Okay? There is no force now trying to prevent him from following. So everything is actually drifting with the same speed because of inertia. The minute the Earth puts a brakes in its motion, let's say, for example, tomorrow, the Earth decides, you know what? I'm not going to go around the sun anymore with 30 kilometers per second. I'm going to stop. In that case, everything on Earth, including us, including people who are sitting, will continue per inertia in the same direction and will fly off. We're not going to be rotating around the sun, by the way. We're going to go in the same direction forever and ever and ever until basically, including the air and everything else. So if the Earth continues with this speed, everybody is really going with that speed. So that's the argument that he was missing, and the argument relies on the discovery of the concept of inertia by Mr. Galileo. I hope I made this point clear in here because it was really a major, major problem at that time. And that also illustrates another point. When you're doing science, you really have to argue your science. You don't have to do a lot of fancy mathematics. You don't have to really know how to do integrals and differential equations and things like that to make the argument for physics. Arguments like this one, they have to be made by physics itself. And the argument, like I said, is inertia. The only reason why the bird can go easily and grab the worm and have no problem with it is because of the fact that it's going to drift while it's going down with the same speed as it was before. Why? Because of inertia. Okay? As a matter of fact, the air also is moving at the same speed too. Okay, and yet we can breathe it and there is no problem with it. Here is another situation. It says you are riding on a vehicle at steady speed and you toss a coin where it's going to land. Then in this case, the same situation as the bird and the worm and all of that before. Because the plane is drifting, let's say, for example, at constant speed, at that point, the coin will maintain that drift speed, whatever the plane is. If the plane is doing 500 kilometers per hour, the coin is going to do 500 kilometers per hour with that one. So it's not going to go back into the plane, but just because of the fact that you throw it. As a matter of fact, you can try this experiment. As a matter of fact, you don't have to go on a plane. You can put your cruise control on the car and you watch your coffee. You're sipping your coffee. You look at it and it's nice. It's not spilling. If you hit the brakes though, or you suddenly accelerate, then say goodbye to your coffee because it's going to go all over the car and you have to go to the car wash the next morning. Okay, so that's basically some of the ideas that were discussed in here. So you really don't need to go on a plane and do this experiment. You can do it in your car and you feel the same thing. Okay. Okay, so this is the content for this chapter. There was a quiz already that you guys are supposed to be working on for the previous chapter. There will be another one for this chapter. Do you guys have any questions for me? Oh, the channel, the links are actually on the discussion session. Jacqueline? So when you go into the discussion sessions, yeah, they will be there. They will be there. And if you want to, and that's a good thing to do probably, because right now I still did not upload the morning class that I taught on YouTube. And when I upload it, it takes a long time to finish, and then I have to edit the captions, and it's really time consuming. So what I'm suggesting for you guys is subscribe to the channel. That way you don't wait for me to give you a notification into that there is a video here, is it on the discussion. Then you probably can go and start watching. You don't have to wait for me to do that, because once I create the discussion, especially the next ones, they will have also rubrics built into them, how they're going to be graded. So I need to finish all of these things to make sure that it's published. So before that, you may have received a notification that there is a new upload. Every upload will have the name of your class first. So for example, if you say PHY10, you know that this is your class. If you see PH4, for example, or PHS or something like that, so you know it's another class, it's not yours. So you don't have to go and basically watch the video or anything like that. So the first words in the title of the video will be the class that it's concerned with. So once you subscribe, you have to pay attention to the titles of the titles of the video before you start watching them, before you waste probably half an hour and realize that he's talking about something that is not our class. So pay attention to that, and then you should be fine. So you can go and subscribe to the channel, and the link is actually on that one. So can we take the quiz yet? Yes, the quiz should be open, no? Can we take the quiz here? Oh, I'll have to check the settings. Karen, you need to get back with me. I'll try to fix it today. If you don't see the problem fixed tonight or tomorrow, you need to get back with me on this one. I didn't know that there was a problem, but I will examine it, okay? Okay. Get in touch with me if I don't fix the problem by tomorrow morning, okay? Because I have another class today, and I have some other things too, so videos and things like that. So if I don't get with you on it, please do, okay? Any other question? No? If not, I guess you have a safe. Yes, the class people who are in the lab, it's going to be at 6 p.m. today. And the link should be also on Zoom. On the class, I'm sorry. Link for that class. Yes, the link is going to be there. So when you go to the lab class, if you are in the lab class, and a lot of you are, the link is on Confer Zoom for where you need to go. It's not the same link. Do not come to this one. It's a different class, different link. Okay? Yeah, we do the labs on Zoom. That's basically, yesterday somebody was joking about soccer, whether or not we can play soccer on Zoom. Okay? Well, for those who I'm not going to see in about less than an hour, you have a safe weekend, and I guess don't forget you have assignments that are due, and we'll see you Tuesday. Okay, bye.